Okay, folks, this is based on a report made by these people, RT of America, on YouTube. Radiation at Fukushima at highest level since meltdown, February 6, 2017. According to them, the reactor number 2 was setting at 500 sieverts an hour. As you can tell, I'm going to do this on iodine 131 to give you some idea of how quick it can go south. If you look at my equation, it's the same equation I've been using. It's the Z equals half-life in years, P equals continuous output of the radiation source, Y equals initial amount of radiation, and D equals amount remaining. Since we don't know the initial amount of the radiation, we set it to 0, and I added in a new equation to reset it once I have a amount available. That's that one right there. D sub 1, D to the nth equals Y plus, in this case it would be X times Z minus 0.5 times Y plus the P to the Z minus 1 over Z plus Z minus 2 over Z plus Z minus Z over Z, which in this case happens to equal the 33,280. Okay. Now what I'm showing here is simple. As you can tell, I've got marked in there 500 units and 192 hours. That's roughly how long it takes for iodine 131 to half-life. Since this equation is based on half-lifing, I had to do that. It ends up with some big numbers. If you look here, right here is the initial equation, initial amount this equation came up with. That's the placeholder. Is 96,000 and minus 33,280, which left us with 62,720 units at the end of the first 8 days. Now this is assuming all 500 units of SEIVERTS being produced by reactor number 2 were iodine 131. In fact, it's not. It's more like maybe about a fourth or something like that. So you would be able to figure out different figures from that. Now, the 158,720 is your Y, which that should be D, not Y. Okay, let's go ahead and change this equation a little bit. The initial amount changes from Y in this equation to D. Okay. I just realized I've done that. The initial amount changes to the previous amount that's left over. So if you have a remaining amount, which is your D, of 62,720 in this case, then you would add the 96,000 that are being added to it on every 8 days. So then you minus 0.5 times that 62,000 plus 33,280. That leaves you with that figure right there. The left-hand figure is the total amount that was produced or was in existence at the time. The 20,000 is the amount that decayed away, and the 159,000, I think that is 456. That's this one right here. No, it's 179,000. Is the amount that remained or would remain if this was all iodine and not mixed with other isotopes. As you can tell, it goes up to 275, then it goes down. By day 30, by the 32nd day, it's starting to decline. All of them are. All the way across. Even the part amount remaining. And by the time you get down here to 72 days, it's back down to 222,000, 96,000, negative 96,000, and a total left over of 123,868. Now what that tells me is that this rule right here is applying. Law of diminishing returns. As you approach the amount of your half-life and your continuous output, as you approach that, which in this case is 96,000, then you're constantly putting that amount out no matter what. There's no piling up anymore. So by 72 days, if this was all iodine 131, you would be at the maximum amount that would be accumulating, and then after that it just simply stays as long as there's a radiation source providing additional radiation, but it won't grow anymore. It continually shrinks until eventually that's whatever number after minus 96,000 equals whatever number, and this would go on for literally 700 million years for a U-235 reactor, which is what number 2 is. So, if the whole 500 sieverts per hour was iodine 131, then this equation would tell you how many units of radiation are being outputted in the end. And it's a huge number. But the truth is that probably is not going to be that high, because you've got a lot of other elements and isotopes mixed in there with that. So I doubt very seriously they'd be that high. And the 500 units per hour, I don't know what the baseline elements are. That's just how much radiation is putting it out. Well, that's what I wanted to show you. Have a good one.